My name is Jolina Jasperson, and this is my extra credit presentation on gradient boosting. Gradient boosting is a type of ensemble learning where we combine lots of weak models, usually small decision trees, to build one strong predictor. Each tree is trained to fix the mistakes made by the last one. That's why it's called stage-wise additive modeling. The goal is to slowly reduce error by minimizing a loss function using something kind of like gradient descent, but instead of updating weights, we're updating the model's predictions step by step. Here's how it works in plain English. Start with a simple guess for everyone, usually the average target value. Then calculate how wrong the guess was. Those are the residuals. Train a tiny decision tree to predict those residuals. Update your model by adding the tree's prediction, but scaled down using a small learning rate like 0.05. Repeat the process, recalculate errors, train another small tree, and add it in. Over time, all those little corrections add up to one strong, accurate model. Here's how the algorithm works. First, we pick a loss function, like mean squared error or log loss. Then we start with an initial guess. The equation says f0 of x equals the value c that minimizes the total loss across all points. In plain terms, we're just picking the starting number, usually the average. Then we loop through each round. First, we find the errors, how far off the model is. Then we train a small tree to predict those errors. Then we update the model. That update formula says fm of x equals fm minus 1 of x plus learning rate times gamma times the new tree hm of x. That just means you take your old prediction, add a small step in the direction, and add a small step in the direction of the new tree. Each new tree focuses on the mistakes of the last ones made. After enough rounds, they stack into one strong model. This is a short Python demo using scikit-learn. I used a dataset called Make Moons, which creates two curved clusters. It's perfect for showing how gradient boosting handles nonlinear problems. I built a model with 200 small trees, each only 2 levels deep, and set the learning rate to 0.05. Then I plotted the decision boundary to show how the model learns where to split the data. The comments on the code explain each step if you want to look at it more closely. The plot shows how the model separates the two classes. The background color shows which class predicts each area. What's cool is how the boundary curves around the data. It's the result of stacking lots of tiny trees, each making little improvements. It doesn't try to overfit with one big complex rule. It builds up gradually. Gradient boosting is really accurate, especially on structured data like tables. It works for both regression and classification, handles messy data well, and gives feature importance on scores so you can see what mattered most. On the downside, it can be slow to train, especially if you use lots of trees, and because each tree depends on the one before it, it's hard to run in parallel. It also needs good tuning. If you set the wrong learning rate or use too many trees, it can overfit. Thanks for watching. That was a quick walkthrough of how gradient boosting works and why it's so useful in machine learning.